All right, everyone, welcome back to Physics 331. So this is part two of the transmission lines video, part two in the transmission lines series of videos. Um, this will be a bit of a shorter video, and we're going to start actually with a bit of a recap of what we talked about in part one. So we were considering a set of long parallel conductors, and we had come up with a model for a circuit model for this geometry, and it was composed of a bunch of daisy-chained LC networks, so the series inductor and a parallel capacitance, one after another. Um, and we did an analysis of this circuit model, and we came up with the wave equation. And we could solve that wave equation for harmonic signals. So if we assumed that the time dependence of the signals followed e to the j omega t time dependence. And our solution of the wave equation is written here for Vz, where capital V represents the amplitude of the voltage oscillations. And there was two terms, a V plus term and a V minus term. And what we determined is that the V plus term, the coefficient was denoted V plus because that term represents a signal propagating along the positive Z direction. And the V minus represents a signal propagating along the negative Z direction. In fact, what I'm going to do is I'm going to go back here, and so we've indicated here a Z axis, and we could set the 0 to be anywhere. And so what I'm going to do is I'm going to choose to set Z equals 0 at the end of the transmission line. And if this line has a length L, then the position over here to the left of Z equals 0 is minus L. Okay, so that's just a choice I'm going to make. It's going to be convenient for what we're going to do today. Okay, we also went through an analysis of this wave equation, and the solution that we have written here was a solution provided we had a specific form for beta. Beta had to be equal to omega, the angular frequency, times the square root of the capacitance per unit length times the inductance per unit length. And we also analyzed what the signal speed, the propagation speed of our signals would be, and they were equal to omega over beta. We showed that for a set of parallel conductors in free space that the speed actually comes out to be the speed of light. So let me do one more thing before we move on. And so if you had an electromagnetic wave, you know that the speed of the wave, say the speed of light in vacuum, is equal to lambda times f. So s is equal to the wavelength times the frequency, and that's equal to omega over beta. Okay, but omega is the angular frequency. It's 2 pi times f divided by beta. And so what we could do is if we take this part of the expression and cancel the f with this part of the expression, then what we can do is we can go and solve for beta. And what we find is that beta is equal to 2 pi over lambda. So that gives us a physical interpretation of beta. 2 pi over lambda is referred to as the wave number. Beta is sometimes also referred to as a propagation constant, but its physical interpretation is it's 2 pi divided by the wavelength of the signal on your transmission line. Okay. The last bit of review is that in the previous video, we kind of highlighted two kind of innocuous results. They were both results for the position derivative of the voltage amplitude. One was labeled number sign, and it was dV dz is equal to minus j omega L times I. And then the other one was labeled as star, dV dz is equal to minus j beta V plus e to the minus j beta z plus e to the j beta v minus e to the times e to the j beta z. And so our starting point is to say, let's take these two results. They're both for the same thing, dv dz, so they must be equal to each other. So we're going to set number sign equal to star. Okay, so minus j beta v plus e to the minus j beta z plus j beta v minus e to the j beta z is equal to minus j omega times the inductance per unit length times I. Okay, so we could solve for the current amplitude, so the current as a function of z, and so that's going to be equal to, let's see, I'm going to factor out a minus j beta, and that's going to leave us with v plus e to the minus j beta z. And because I factored out a minus j beta, the second term is going to have a minus sign minus v minus e to the j beta z. And then we have to divide by minus j omega times the inductance per unit length. Okay, so there's some obvious cancellations. I guess the minus j is going to cancel. And that leaves us with an expression for the current amplitude. Before we write down that current amplitude, I'm going to define, let's see, I'm going to define z naught is equal to omega times the inductance per unit length divided by beta. But we know that beta is equal to omega divided by times the square root of inductance per unit length times capacitance per unit length. And so therefore the z naught that I'm going to define is equal to the square root of the inductance per unit length divided by the capacitance per unit length. And so this thing has a name. This is called the characteristic impedance of the transmission line. And so if you think back to the example we did of parallel wires, the inductance and capacitance per unit length were just determined by constants and geometrical factors. So this characteristic impedance Z naught is just determined by the geometry of your transmission line. The reason it's called an impedance is because the units of Z naught, if you work them out, are equal to ohms. Okay, but anyways, this quantity, omega times the inductance per unit length divided by beta, is exactly the inverse of the coefficient of our current amplitude expression. And so therefore what we have is I of z is equal to 1 over z naught times v plus e to the minus j beta z minus v minus e to the plus j beta z. And so this is our expression for the amplitude of the current at any position z along the transmission line. So this is the amplitude of the current at an arbitrary position z along the transmission line. And so you could compare this to the voltage amplitude that we calculated last time. So last time, we determined that from the solution of the wave equation, the voltage amplitude at an arbitrary position z was, it looked similar. It didn't have the coefficient out front, and then it had a positive sign between the two terms. Otherwise, it was the same. In fact, I mean, from this equation in the box here, you could verify that Z naught definitely has units of ohms, because we're saying that the current amplitude, which is measured in amps, is equal to a voltage V plus or V minus, a voltage amplitude, divided by something Z naught. And so that Z naught has to have units of ohms, so that volts divided by ohms matches the current units of amps. Okay, good. So maybe before I move on, maybe the one thing I'll say just in words here is that for the coaxial transmission lines that we use in the lab, in the Physics 331 lab, Z naught for the coaxial cables is also just determined by the geometry of the cables, namely the inner diameter of the center conductor and the diameter of the outer conductor, as well as, I guess, the material that fills the space between them. And those coaxial cables are designed to have a characteristic impedance of 50 ohms. So maybe I'll just write that down. So for the coaxial cables commonly used in the lab, Z naught is, this is probably a bad way to say it. The cables are designed such that Z naught is, maybe I'll rewrite that. The cables, let's see if I can make this better. The coaxial cables commonly used in the lab are designed such that Z naught is equal to 50 ohms. And that's going to be an important thing. I think we'll see why in maybe in just a few moments. Okay, so the next thing we're going to do is we're going to consider a transmission line where one end is driven by a function generator. So the signal it outputs is some harmonic signal, some sinusoidal signal. But then we're going to take the other end of the transmission line and we're going to terminate it with a load impedance. So it could be a resistor or an inductor or or a capacitor or any combination of those things. So it has some effective impedance ZL at the position Z equals 0. And so remember, we set Z equals 0. We said we were going to put that at the end of the transmission line. So what it looks like then is we have a function generator connected to our transmission line of some length. It has a length L. And then over here at the end, we're going to connect some impedance ZL. And it's, so like I said, that's some combination of resistors, inductors, and capacitors. And so over here, we set this to be the position Z equals minus L, and this is the position Z equals 0. And so if we were to measure the voltage at this end, this would be the voltage at Z equals 0. And then we would also have a current in our load impedance, which is the current at Z equals 0. Okay. In other words, the voltage and current, the voltage and current at the load impedance ZL, which corresponds to the position Z equals 0, are given by, well, okay, here's the voltage. All we have to do is set Z equals 0. So V at 0 is equal to just V plus e to the 0 plus V minus e to the 0. E to the 0 is just 1. And so we just get V plus V minus. And so you can see why it was a convenient choice to set the origin, in this case, of Z to be at the load impedance, because we get a really simple expression for the voltage amplitude at the load impedance. Okay, and likewise, the current at the load impedance is just the current at Z equals 0. And so we just go back and look at our solution for the current amplitude. It's 1 over Z0, and then it's going to be V plus minus V minus. So we get 1 over Z0, the characteristic impedance, V plus minus V minus. Okay. So by definition, if we know the voltage and current at our load impedance, then the value of ZL has to be VL divided by IL. Like if you take the ratio of the voltage across of our impedance divided by the current in our impedance, that has to be equal to ZL. Okay, but we have simple expressions for these things now, and so it ends up being V plus V minus divided by V plus minus V minus, and then we still have a factor of the characteristic impedance. Okay, so what we're going to do with this is we're going to solve for the coefficient V minus. And so let's see, what's the best way to do that? Well, we'll go ZL times V plus minus V minus is equal to Z naught V plus V minus. And then what we'll try to do is we'll try to put all the V pluses on one side and all the V minuses on the one side. So I think we're going to get a V plus ZL minus Z naught is equal to V minus ZL plus Z naught, if I've done this correctly, so that when we solve for V minus, it's going to be equal to V plus times, let's see, ZL minus Z naught over, over ZL plus Z naught. Yeah, I think that's right. Okay, and what is conventionally done is this ratio of impedances, the difference between ZL and Z naught divided by their sum, is defined to be gamma, capital gamma, and that is referred to as the reflection coefficient. And so with that notation, then we can say that this V minus coefficient is equal to gamma, the reflection coefficient, times V plus. And so you may have wondered in the previous video, when we started talking about signals propagating to the left along, well, let's say signals propagating along positive Z and also signals propagating along negative Z, like what was the origin of the signals that were coming back along the negative Z direction? Well, their origin is if you have a function generator, a signal generator, sending signals out to the right along positive Z, the signals that are returning along negative Z are due to reflections at the end of the transmission line. And how much of a reflection you get is determined by this reflection coefficient gamma that we just calculated. Okay, so if we were to go back and let's say we label this as VG, our signal generator. So it's outputting a signal of amplitude, capital VG, I guess. So a signal incident, let's say from the generator VG, which starts out in the plus Z direction, is in general is partially absorbed by ZL. So some of the signal is going to be absorbed and some of it is partially reflected, and that reflected signal is propagating in the minus Z direction. Okay, let's just look at a couple of cases. So let's examine this reflection coefficient. This will be the last thing we do today. Okay, so let's just remind ourselves what it looked like. It was ZL minus Z naught divided by ZL plus Z naught. So a couple, let's call them special cases. Special cases. 1. Well, we could have ZL equal to 0. This would be a short circuit. So let's suppose then that at the end of the transmission line where we said Z equals 0, that position, we just take the center conductor, well, if it was a coaxial cable, we take the center conductor and short circuit it to the outer conductor. If they're parallel wires, we just connect the two ends. So that would be a short circuit with a load impedance of 0 ohms. And in that case, gamma is equal to 0 minus Z naught over 0 plus Z naught, which is equal to minus 1. And so what minus 1 means is that you have first of all, a perfect reflection, but the negative sign means that the signal is inverted. And I think in maybe a future video, not too long down the road, I may try to set up some demonstrations to show you this. So in this case, we get a perfect reflection, but the reflected signal is inverted. Okay, special case 2 is ZL goes to infinity. So this would be like an open circuit. So we just connect nothing across the two ends of our wires at Z equals 0. They're just not connected at all. So in that case, gamma is going to be ZL, which is infinity, minus Z naught, divided by ZL, which is infinity, plus Z naught. And of course, the Z naught is insignificant compared to the infinities, and so we just get a plus 1 here. We just get ZL divided by ZL, which is plus 1. And so this is just a perfect reflection. Perfect reflection with no inversion of the signal. Okay, the third special case, which you might have already imagined, is we can set ZL to be equal to Z naught, the characteristic impedance. So remember, for a coaxial transmission line, we said that was 50 ohms. So if you take a coaxial cable that we have in the lab and you terminate one end with 50 ohms, then any signal incident on that, well, what happens? Well, gamma is ZL minus Z naught divided by ZL plus Z naught. But we're looking at the special case where this goes to Z naught. And so this is equal to Z naught minus Z naught, which is 0, over 2 Z naught, which is just 0. And so the reflection coefficient is 0. You get no reflection. And you get the signal is perfectly absorbed by ZL. So this is called impedance matching. If you match the load impedance ZL to be equal to the characteristic impedance of the transmission line, you'll get no reflections at the end. And so that has lots of important implications when you're setting up experiments, especially when you're setting up experiments at, say, high frequencies. Okay, so that's where I'm going to stop for today. Thank you very much, and we'll see you next time.